Okay, and we are live. I think we are live. Should be. Nice. Okay. So the stream I will make here. I will start in 5 minutes as usual. Hello, blogger. As usual, I will be sending you the codes because I don't have the login information for the competition. Tell me if something is wrong with the stream, if something goes wrong. Okay, so that's pretty much it. Today we're going to solve the rope problem. I call it tiles problem always for some reason. And I asked, so the last time we were looking at the problems from the JBOI, so from this Olympiad, right? And we kind of found the solution for tiles. We also found some kind of solution for magic, but I will tell you a little bit about some cases that we need to think over. But I've drawn here a case where we discussed this case last time, where if a rope starts from some position here, it goes like this and goes like this. Is this possible? This is actually not possible. You are supposed to if you enter here, you are supposed to only exit here because this segment allows you to only do that. So this segment only connects this point here with this point here, and also this point with this point. And there are 3 types of tiles. This is the rotation 1 tile. There's 1 tile with not on the other side rotation, and this is like the connect tile for connect this cross tile. If I open up the problems, I will put the problems in the chat. Where is this? So we're going to be solving this problem. Should I put it on the chat or should I put it in the description? Maybe in the description would be better. So problem, this is magic, and the other problem was rope. So there we go. The links to the problems should be in the description right now. We are going to be solving this problem rope first because it seems like a heavy implementational problem and I want to solve this. Tomorrow there's CERC, so this is a regional competition. CERC 2023, this here. Oops, not 2023. This is the Central European Regional Contest 2023. It's actually from today, but today is just an empty day. It's tomorrow, and the day after. So we actually in Sunday there is going to be the competition. Tomorrow is just a practice day. It's a 5-hour ICPC ACM contest, of course. ICPC rules. Should be fun if someone is there, if someone is on CERC. I maybe should write in the description tomorrow is CERC. If someone is there participating, come and say hi. Yes, so if somebody's participating, it should be fun. It should be a fun contest. I mean, it's not. There's a lot of problems, and usually you just solve a couple of problems. It's really hard contest, so yeah. Okay, okay, let's go to the problem. It's already 6 minutes in the contest in the stream, so I can just go through the problem. So again, let me read again the problem. There are n by n cells, square cells, each of these 3 types. Type 1 is this rotation, type 2 is this other rotation, and type 3 is the cross cell. And there you can create some ropes. So you can create some ropes that start at some ending point at the top, at this edge of the board, and end at some other ending point. And now there are a couple of different subtasks that you need to solve. P1 says you want to only count such configurations where you have at the edge of the board you have some tiling like this, or you have some square which is rotated like this. So this is just the count of these configurations for P1. For P2 is the output, the length of the longest rope with extremities on the edge of the board. So the longest rope with extremities at the edge of the board. So you have to kind of you have to calculate for all of the ropes and see which one is the longest. And out 3 is the most difficult subtask, where you need to output the length of the longest rope with extremities on the edge of the board that can be obtained if a type of exactly one tile is changed, and the number of ways of achieving this maximum. Note that if a tile can be changed in 2 ways to achieve the maximum, it comes up to 2 different ways. So what you want to do is you want to iterate through all of the tiles for the third case. You want to iterate through all of the tiles, and you want to try to change to another type of tile. And when you change to another type of tile, at most 2 or at most 4 different paths will be I think at most 2 different paths will be 4 different paths actually will be ever changed, and you just want to figure out how you what is going to be the longest rope after changing this one tile. Okay, so let me start coding this. Let me start coding this. Code what is this rope? CPP. We are going to do this. There's N and there's P, as far as I know. 2 integers N. So there's first P and then there's N. P, N. Then there's some vector of N strings. And then there's, so I will create maybe it doesn't really matter. So I will create this. If p is 1, then I have to only iterate to find out this count of this thing here and count of this thing as far as I know. So p is 1, I'll put 2 integers, count of v-shaped rows at extremities and count of these rhombuses. Okay, so v-shaped rows and the extremities and rhombuses. That's so. Yeah, I thought about making a function for every case, but seems okay. Let's do it. I mean, it's a bit, I think, necessary, but solve p1. If p solve p1, okay, here you go. So I will go through each of the rows here on this side. On this side, you would want to say that if a of I of 0 is equal to this type 2 and a of I plus 1 of 0 is type 1, then v shape plus plus. Also so you can just check here immediately because it's a square matrix. So I can say if a of I equals, so this is for this, I will do this first. A of n minus 1 is, this is supposed to be 1, and this is supposed to be 2. And now the same idea, but with here, this is supposed to be 2. This is supposed to be 1. If a of 0, if a of n minus 1, I is supposed to be 1, a of n minus I plus 1 supposed to be 2. Oh yeah, thank you Blogger for this. Okay, so that's pretty much for this, and then there's one more thing that we need to do, and that's the rhombuses count if a of I of j is equal to 1 and a of I of j plus 1 is equal to 2 and a of I plus 1 j equal to 2 and a of I plus 1 j plus 1 equal to 1. And then we need to output two things, v and r. So that should do it for the first test case. solve P2, P3. The rhombuses are not correct. Wait, how? Yeah, that's 1, 2, that's 1, 2, then that's 2 again, and then... Oh, it's not correct because, again, this... I forgot about that again. Okay, so that's P1. P1 should be fine. P2, P2 is, I'll call it, so P2 is a little bit more complicated, but actually P2 and P3 I kind of want to call it in one function. Or should I call it like a data structure that will allow us to do that? No, I want to make it recursive. No. I just won't make it recursive. I want to know how many points it will get. What do you mean recursive brute force? I mean changing some tile and then computing everything again. If you do that, like, I mean, that's, I don't see a, I mean, that's a nice step. That's a nice subtask that you will probably has something here about this subtask. For P2 you don't need recursive. I will show you how to code this. For P2, there's no need to be recursive. What you will do is like, I mean, you can do it recursively. It will be the same. It will pass again with everything, with every test. It won't be slow at all. Yeah, like everything will be fine. But what I will do is I will create another matrix that will present up these points here. Like every of these thing here will be like a node in some other matrix. All of these will be like nodes. You see, this can be represented with another matrix. If I take these and I shift them like up here, you see this is like another matrix. So this will be like 0, 0, this will be like 0, 1, this will be like 1, 0, this will be like 1, 1, and so forth, right? This is another matrix, and each tile represents only like an addition of edges between these two nodes. So here, like you add some edges, here, like you add some edges. Here, let's say you add this kind of edges, where like you do this, right? And then here, like you add this, here, like you add this. And what you do is like just, I mean, either just push DFS or push BFS. It doesn't really matter. You just start here and you just go through the edges, right? And for each node, I kind of want to know how far am I from the start. Every cell is a 3 by 3. Every cell is 3 by 3. I don't know why would you do that? I mean, 3 by 3. Yes, but you have duplication here. Like you have to. It is possible. It is possible to do that. what you can do is like, if you want this node to be in both cells, like in here and here, it is possible to, let's say that these are two, let's say that there are like 4 cells. Okay, let's split them up into 3 by 3. Doesn't quite matter. It is possible to have this node and this node already connected by some edge, and this edge will have weight of 0, while this node and this node, if they're connected, will have a weight of 1. And then you just want to know how what is the weight of this path. What is the weight? This is also possible, but kind of, isn't this much more complicated to call than this? I mean, you have to add these additional edges. You have to also know for each edge what is the weight. But it's, I don't know, if you don't do a graph, I mean, it's still like a graph, right? So like, I mean, when you change something here, when you change these two connections, you will still need to calculate the path to here, and then I will call it this way because I think it's simpler just to call it, it's simpler to call it like this. But I'm not sure, maybe the official solution also takes into account some like additional nodes here between, like you can split this node into 2 nodes, essentially. One node on this side and one on this side. And then it might be easier to find some ideas. But always when you take a look at some tiling problem which has like these connections, it's always like a graph, and is either it uses some DSU or it uses some kind of greedy technique that, like in this problem, like you don't have to reattach this, but you need to only know what is the length of the rope there. So it's kind of either DSU or either this. But what I want to do is I want to solve both of these P1 and P2 cases with like the same pre-processing. So maybe I will have like a struct where like I have like a graph, and then this graph will have and then I have like pre-process. To pre-process, I need to create a vector of these nodes first, right? Kind of need the nodes to create them, so they are like how many nodes are there actually? There. Hello, Victor. How many nodes are there? There are, so for each of these rows, there are n plus 1 nodes. Imagine this is an auxiliary node here that's never used. There's n plus 1 nodes, and there's n plus, is it n plus 1? No, it's much more than n plus 1. So there's n plus 1 nodes for all of these, but then there's, for each cell, for this is 2 nodes, so there's 2 times n plus 1 rows. What if I do it like this? What you said 3 by 3, but like... Would this be better with indexing? I don't think so, right? How many nodes would there be? There will be two n plus 1 nodes here, like this. 2n plus 1 rows. So making columns and rows the same. I mean, no, like if it depends on how you look at the problem. You can look at it like this, because if I shift all of these like that here, it becomes that only there are n columns, but the rows are still the same. So like you can shift all of these here. The rows are still the same, but you can shift it the other way around. The only thing is that I think you can do it to n plus 1 and to n plus 1 if you just imagine that there's like all of these as well, like 3 by 3 something. So if it's 3 by 3, then it's like 2n plus 1 and 2n plus 1, and this I think it could be also cool. Yeah, let's do it like this. Let's do it to n plus 1 times 2n plus 1. So there's like, the rows are 2n plus 1, and the columns. So rows are 2n plus 1, columns are 2n plus 1. Also, we kind of want to have a... Okay, so we want to have a function where given a point, where given x and y coordinate of a tile, it finds all of the corners of this tile. So all of the get corners, let's call it, and there's this function, let's say all of the corners. So the corners will be, so I need to center this tile here at the center of this. So if I have, this is 0, 0, this is 0, 1, the tile is at 1, 1, then this is at 2, this is at 1, 2, 3. So it kind of seems that this is just offsetted by 1, 1, right? So it's essentially the corner is, one corner is I and j plus 1. One corner is, so this is I and j plus 1. So to do this is, I'll make it simple here. Actually, I can do this dx d4, and then Is this correct or is this? Well, yeah, this seems to be correct. dx d, and then output push. Okay. Yes, I'm taking the center of the cell, and then I'm finding which is the left node, which is the right node, which is the top, the bottom. This all of these nodes I'm finding them. So these are the nodes that are from the center up, left, this and that. And this is shared node. So this node is shared between these two cells. That's why I don't have to skip a cell. Essentially, if I look that all of these initial cells are here, right? So 0, 0, 0, 1. I mean, in a ordinary, like if that's the beginning of the cell, I just shift it here to find this cell, and then from this cell I can go left, I can go top, I can go this, and I can go this. So I find like these corners of the cell, and then when I have the corners, I just have to connect them. So there's are two things I need to do. I need to connect tile 1, I need to connect tile 2, I need to connect tile 3, right? So let's see this. So let's say that so the corners, we know which of these corners are this here. So the corner, this is in the y direction -1, which means the column direction. So this is left, this is right, this is up, and this is down. So so I can make a tile 1 how is it this? Should I hard code this? Okay, let's hard code this. Connect 1. So tile 1 connects corners. I mean, yeah, that could be also, but then debugging is kind of a pain in the ass, right? So I mean, I don't like representing them with IDs. Debugging comes and eats time afterwards. But yeah, that, I mean, corner and this can be, you can add a function. So tile 1 connects left with top. So there's like connect corners 0, corners 1. Top is not 1. Top is 2. Corners corners 1 and corners 3. Connect 2. Connects corners left and corners bottom. So corners 0 and corners 3. Corners 1, corners 2. Connect corners left and right. So that's corners 1, corner 0 and 1. Now the connect function is just taking taking corner C1, corner C2, and saying, so there's some adjacency vector here. R times C. So we kind of need to convert them. Get ID. Return x times r plus y. That's the ID. Kind of need to kind of get adjacency at C1 get ID. Push back C2 get ID. And we need to get the other way around. No, I don't say it worse than. So we need IDs to linearize them into vectors, but the whole idea is to have them in integer form as well, not to convert them in IDs very quickly, because I can here, of course, I can debug it. I can print. If I print ID, I mean I will need to convert it back to integer form. I don't know, however you want to call it, it doesn't matter. It only matters to work. So we connect these two, right? So we kind of connect them, and then now we have to go over the tiles and say pre-process. Yeah, that I will do. I will do. That I will do from ID. The pre-processing should be simple. If the pre-processing should be simple, and now we need, after pre-processing, we kind of need to say that find the length of the ropes. But the length of the ropes is, what I will do is I will start yeah, let's call it with a DFS. It kind of doesn't matter what you call it, but So if v is parent, then we continue. If now we say DFS at v, v node then plus 1, then this is, we say that in this node it's kind of, so we kind of need to process the length. But when we are at some node, we can go either to that side of the node or to that side of the node. So we need like two lengths. One length from one side of the node and one length from the other side of the node. If I'm here, when I flip this, how is this best to implement it with a small amount of code? For this subtest for P2 it doesn't matter. You can just go and you can just find the path. Doesn't matter. But for P3 it does matter. Because when you switch, you have to know where you have switched. So do we solve first for P2 separately or for both at the same time? So for P, maybe just do P2 for now. I mean, okay, like, for P2 is like, okay, DFS1. For P2 is this. For P2 is this. You just DFS, you find this route, you return this number, because we know that there will be only one connection, so this is just return, doesn't need to be maximum, doesn't need to be anything like that. And that's pretty much for P2 for the DFS. So now I will do another function as I will say iterate corners. And there will be like iterate corners, and this iterate corners will iterate for all of these corners here. That's what I meant by recursive brute force. I meant doing DFS. Yeah. I mean, yeah, it should work. It's linear time, just passing through these edges, and that's it. Let's iterate through the corners, and we'll test it out. And if it works, I will submit the code for P1 and P2. Then we'll update to P3, make another function that will update it to P3. That doesn't matter. Okay, so let's, how do we iterate the corners now? The corners are, the corners are this here, but essentially, so the corners are I0. Because there were three paths that you can go through tile type of tree. Yes. I understand. But there is just one path. You can go there too. So let's do like this. This is corner 1. This is corner 2. But actually, because we start from here 0, 0, this corner is like 1 shifted, and this is 1 shifted again. So this is +1, this is +1. The end corner is actually shifted, and then shifted 1 again. So this is like n +1. Because this is shifted here, and then 1 more time is shifted here. So that's here, and then you have the same idea, but it's like the other way around. So all of these corners should be checked. Now, of course, I cannot check a corner. I can only check I will answer is max of answer and DFS1 C1 dot the parent is -1 here, C1 dot get ID. Longest. And now we're gonna create a graph, then with N and A, then we're going to pre-process, right? This will connect the graph, and we're going to see out. That should kind of work for test case for this. Okay, doesn't work. When I wait. This is what is the case? That's pretty suspicious. That's pretty suspicious. C1, C2, C1, C2. Let me. Okay, let me just draw how this should be connected. I mean, I want to draw the whole thing. I'll just draw this first couple of. See if the connections are right. So the 1, 0. So first is 2. Layer 2 is like this. 1, 0 is connects with 2, 1. So this is 1, 0. It connects with 2, 1. This here. That's correct. 1, 2. It connects with 0, 1. 1, 2. It connects with 0, 1. That's correct as well. Okay, that's correct. Okay, the connections are correct. How is that possible? Now IDs. Who knows what IDs is this? 23. Two, 1. 2, 1. This node is connected to what? This is 1, 1. To 11, 13, and 35. There's no way this is connected to 35. I have no idea what is 35, but that's not. that's not a node. 3, 2, 1, 2, 1, 0, 1, 2, 3, 2, this. That's no way that this is connected. Okay, this is 1, 0. 1, 0 is connected. 1, 2. 1, 2. No, it's not connected with 1, 2. 0, 1, 2, 3. This is type 1, 3, 2. Type 2, type 1 is like this. Type 1 should be like this connected. So this 2, 0, 2, 1. 2, 1 should be connected to 1, 0 and 3, 0. Have I missed something here? Corners at 0, which is left. Corners at 2, which is up. Corners left. Oh, where it is missing? This is not supposed to do that. This 2, 1, 2, 1. Where is 2, 1? It connects to 1, 2. Then it connects where else it connects? 2, 1. It connects to 1, 2. 1, 2. Oh, get corners of, wait. Get corners of I and j is get corners of I plus 1, which is, that's here, right? No, 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 no. It's not this. It's, the center is not here. The center is, 2 times I plus 1. J is 2 times j plus 1. That seems correct. Am I using the center somewhere else? I'm using the center here, am I not? I'm kind of using the center here. That's 2 times I plus 1. 2 times, and that's n minus 1. That's a center, and then we're adding. So 2 times I is not the center. Two times I 0, 2 times I, and then here 2 times I minus 1 is the center, plus 1 is not the center. Then 2 times I plus, that's not, 2 times I plus 1. Yes, 2 times y plus 1 is the center, 2 times I plus 1 here, and this is 2 times n minus 1, which is the center, plus 1, it's not the center anymore, 2 times I. I think that's correct, but I'm not sure. Right, let me check again. Let me see. Okay, here that should be okay. Here that should be okay. Here that should be okay. Okay, the only thing I need to check is this. So 2 times I plus 1 is the center, right? On this point, which is this correct. And then this is also the center of the last, but we want plus 1 because we don't want the center. Oh, no, this is the center. We want plus 2. And here also 1 plus 2. No, not here. This is the center. This here is the center of this node, but this is plus 2, I think. Yeah, so I think this is, I will submit this. I will submit this to see if that actually works for P1 and P2. Maybe it won't work. I don't know. Maybe I have some mistake here. The corners. But for P3 it's a little bit different. For P3 I have to kind of do some clever implementation. We have to oops. Why did it judge? $48 points. What does 48 points mean? But where is 48 points? I mean, oh, I have wrong answers on some small cases. But okay, this is wrong answers is fine. Memory limit exceeded. That's not fine. And time limit exceeded. That is not fine as well. Okay, I mean, wait. I'm not okay. Time limit exceeded should be fine because time limit exceeded kind of. I'm not returning anything here. Or maybe it's not supposed to be like that. The wrong answers, not really sure. So 48 points. What is 48 points? I'm not sure. There are 10 cases where P is 2. And 10 cases where P is 3. So cases where P is 3 is fine to fail. Do I have some wrong answers even on these small cases? Let me try something. P2. This rhomboid structure, how this is created such that it's like 1, 2, and 2, 1. That's correct. There's 1, 1, and 2, 2 should be one of these other structures. This is interesting example. This is 2, 2, and 1 like this, and then there's 4 of these structures, which is correct. I don't know, the small cases could be also just these input cases. 3. Yeah, these are the small cases. It's just the inputs. So, okay, so I think we kind of pass everything, maybe except like these huge cases here. What is 2 times 2000 times 2 times 2000 and times 4 bytes? 64 megabytes. It could be due to the vectors actually. The vectors may be like very slow, very memory intensive. But other than that, I'm certain that there's like if all of the vectors, if all of these are up to 2 points, 2 bytes, which means that there's only 100 and yeah, all of these instead of a vector, I will just make it like a pair of not a pair. I will do it like adjacency at like this. Now I don't have to use vectors. And I will say adjacency int u is this. And then see, I need some kind of I need adjacency at u at p of u. I can optimize this as well. I'll need actually P. I can optimize it with which is the direction. But it shouldn't supposed to take a lot of memory. This should be super memory efficient. So there's like this P means how many adjacent things it has, right? So this is the maximum size times 4 bytes each times 228 megabytes. How many megabytes do we have? 512. That's supposed to be good. Okay, so 512 megabytes. So here we are just going to say P of node if int v is adjacency of this node I, if what is this now? Why is this? Adjacency size, I will call this. So not to be confused with parent. Okay, so if v is equal to the parent, we just continue. Otherwise, we return here. And I don't think actually DFS is the right way to go, but whatever, because this is slow. But it should be good enough, I don't think. Okay, so memory limit exceed. So now it shouldn't limit exceed at all. That should be fine. I guess corners, but corners is fine. This can be optimized as well. What about now? Let's see if the time limit and the memory limits are fine. This should do it in linear time. I don't see another way of optimizing any of this here. Okay, we got 60 points. That's nice. That means that we have P1 and P2 fully solved. Now P3, and it's super fast. Of course, an example fails because P3 is not implemented. But okay, so how do we implement P3? The memory usage is about 200 megabytes as far as I can see, so it's fine. So how do we implement P3? For P3, we need very fast to switch one tile, and we will switch them to every tile that is not the tile itself. Yeah, I know. So it everything passes. P1 and P2 passes, but P3 doesn't. So I mean, it's fine. It's totally fine. We solved it, but for P3 now we need. Okay, so the change. So we need P3. P3. Let's build the graph. Let's do pre-process on the graph. And let's go over all of these end nodes. And now we need to know, we're gonna iterate over all of the characters. If a of I is C, continue. It's actually 1, 2, and 3. But then change a of I j to CJ, CH. What happens when we change? When we change, first we have to remove the edges added. But we don't have to actually remove them. If we pre-process, if we have another vector that has like pre-processing inside for each of these edges, we kind of don't need to remove them. We don't need to remove them at all. So what happens here? What happens here? If I go like the problem is with our approach here, we're using a little bit more memory than what we actually need, and maybe at a later stage we would. So my approach here, the first thing what I said about shifting these is kind of very memory efficient, because we are using only n times 2n nodes. This is the amount of nodes we actually need. But now here we're using 2 times n times 2n, so we have one more 2 factor in front. We can put this 2 factor away if we're clever, but for now it's fine. For now it's fine. Let's see what happens when I change something. Let's copy this. And let's say that, so there's some, let's draw more nodes here. And our case was that, okay, let's draw it like this maybe. It doesn't really matter. What happens if I change this node to something like this, or something like this? First, the length of the rope, we're only interested at the maximum length of the rope by changing. And we are, what it says, change the type of exactly one tile such that the length of the longest rope with extremities on the edge of the board is maximized. Also compute the number of movements that ways that this can be done to maximize this length. So when I change this to that, I care about at this node what is my left rope length, and this node what is my other rope length. That is going like this. At this node, what is the rope length here? At this node, what is the rope length here? Then I can combine these two and these two. So for each node, I want to know what is the rope length coming into this node here. So the rope length coming into, seeing from this side and seeing it from this side. Need to update the pre-processing right now. I mean, not to update the pre-processing, but the DFS, when we run the DFS, for each n by n nodes, I will remember on the four corners what is the length of the rope ending at that corner. I'm gonna do this. And now when I have it pre-processed, let's assume that we have it pre-processed. When I change to something else, what it will do is, if CH is 1, what we're changing is we take pre-compute at ij and 0, 2, 0 plus 1 plus pre-compute Is it possible? Is it possible to form loops? I mean, it's possible to form loops, but is it possible to so you have some loop. Now if I close it, so let's say you have some so it has to start somewhere, it goes somewhere here. So let's say that I close it such that I connect something to here. And this would make this and then this. Yeah, okay, I mean, I think it's fine. I think it's fine. Pre-compute at 0 at 1. This is the maximus. Zero and 2. 1 and 3. Zero and 3, 1 and 2. Then 0 and 1, 2 and 3. And this Umax function will be just this one. So set the current length and the count of this. How many times we have seen the current length, and then we need to output them. Output the length of the rope and the maximum number of ways of achieving this maximum. So current length count. This is the best length, not the current length, the best length. Pre-compute oh, we need to get coordinates here. We can just do this. I need coordinates. So pre-compute. Okay, so we have this. This is fine. Now we need to pre-compute this. And the pre-computation should be in this function, longest. We're calling this function here just to pre-compute it. Okay, this is a terribly just the implementation we have a problem. Just terrible. Okay, how do we compute this? For each node, so I'm at some box. I can calculate at what box am I, right? True, yeah, well, so I'm at some box. Then when I go here, I want to update the pre-computation of this box with something here. So I'm at some box, and when I move, I always end up at some other box. So I have to kind of know where I am. I kind of have to know where I am, right? So I always move to some other box. But now I have to find how do I calculate this box that I moved to. What is the intersection between some node I moved to and myself? There are there are coordinates that I need to get. Not coordinate. Let's avoid using coordinate because that's not a coordinate. That's a box. I need an intersection here essentially to compute that because I don't like if statements. The only thing I want to avoid in this problem is if statements. I want to make it everything with for loops. Here, like you see, there's no if statements. This is an if statement because you need to call different functions, but there's no if statements. Let's just think about this intersection. This is more of a functional programming approach, if you have heard of this. Like you just want to do everything with for loops. So I have a node and an intersection. And I have a corner here that I will move to. I know this corner. And I'm at some box. And now I want to know which box has this corner. So I can iterate through all of the boxes, all of my four other boxes, and I can find which one has this corner. And this is the most easy approach to come up with. So intersection between some corner C and some box which is represented by x and y. So I want to know this intersection. So instead of, okay, let's do a box here, B. I know it's the same structure. I know that this will have like the same thing, but trust me, it's much more clean if you do this. So I know what is a box and what is a corner. So this is a box, B. And I return a box here as well. So an intersection will return intersection between my corner, which is corner from ID and node, this is my corner, and the box, where, no, my corner, this is not my corner, the new corner, and where this box is. So that's so I get the new corner and my box, and now I need to iterate through all of the boxes which are in my vicinity. Box.x new x there, box.y plus new y there. Now the boxes, so if nx and ny and nx is smaller than n and ny is smaller than n. So if I'm all inside, I have some center, which now center is nx and y, and I need to, this center, I need to iterate again through all of these other boxes, through all of the corners of my box. But this can be also, I mean, this can be also pre-computed, just, I don't like if statements, I'll just iterate like this. If this takes too much time, I will optimize it. But it shouldn't take too much time, because as soon as I find the box here, that will be this, I will just break. So so this is my, no, I will just do this get corners. Get corners nx and y. So this is the corners, and I will iterate through all of the corners and see if they match. If C1 equals to C equals, I can just make an operator. So if that's the case, if my corner is equal, then I will just return the box which is represented by nx and y. And there should be one corner which has this. So I will have this intersection. So there's no if statements here. There's this beautiful code. Okay, so I get the intersection. So I know where I am. I know where this box is. Then the idea is just to say, okay, the idea is just to keep the length which we started with. And the idea is just to say, okay, the new box is this, right? Pre-compute at the new box dot x, new box dot y, And now I need the corner as well, so I need to return here a box and the corner ID. The corner ID is here. Oh. The corner ID is, I return the box and D2. This is corners at D2. So that's my corner ID. I return the box and the corner ID. This is the length. The length is +1. Okay, so and then we say that this is the new box. This is the new box I'm going in, and the length is updated, and the length that I'm returning is also updated. But this is cool. So I have the intersect. I go to the next box. I update it there. I have pre-computed everything. That should be pretty much it. We start from everywhere. We pre-compute. Now here, P1 is -1. The box where we start is the boxes here is a little bit complicated. I plus here, then the length is 0, of course. Here is I and n-1. Here's -1, 0, and I. Here's -1 and -1, I, 0. So that's pretty much it, I think. It never works at the first time, so. Okay, I crashed the DFS here. Is it something that doesn't return -1? Oh, when I go outside of this, then I kinda if new box ID, if new box X is not -1, I kinda don't want to do that. Wait, what? What is this? Where is this? Oh. 23? There's something with 23. There's no way something is 23. This got 14, but it got only 1. Zero, 2, 0, 0. 23. Do you know what is like 23? We can get up to by changing the highlighted tile. We could also change the tile The tile in row 1, column 1, type 1, thus we output 2 ways of changing maximum 22. What is the tile we should change? By changing the highlight tile, we could also change tile type to type what? Type 1. Probably like this something. Type 2. Wait, that doesn't make sense. From type 3 to type 1. Type 3, that's not... Oh, that tile. Oh. Wait, I don't understand here. I'm not following this. By changing the highlighted tile, we could also have changed the tile on row 1 and column 2. So this is what it looks like, and if I change this tile, it is 22. Okay, I don't quite. Not sure. If I draw, what tile am I changing here is the problem. What tile am I changing? What tile do I have updated? 01 changes. 01, yes, it does change to 22, but 33 changes to 33 changes to 23. 3, 3. This tile. Wait, this tile is. Wait, 3, 3 is this tile. It's type 3, and we want to change it to something. One, 2, 3, 4, 5, 6, 7, 8, 9, 10, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. Oh, when I change it here, oh, I see where this is wrong. Oh no. I think I see where this is. No, I don't know if this is the original. It's just so stupidly drawn and nothing is. But the trick is that, okay, see this, like this tile, this is a loop here. And, okay, I calculate for this node what is the length up to here, right? You calculate for this node what is the length up to here. You calculate for this node what is the length like this, and you calculate for this node what is the length like this. And you see, this node and this node, when they are connected, you have twice this length, which is the loop between these two. You have one time you go like this, and another time you go like this, which is not correct. This is counted twice, this 3 here. When you connect these two. But it only should be counted once, because, I mean, it only should be a loop here when you connect these two. Because this guy kind of overturns. I'm not sure, does this happen only on like type 3 node? Type 3 tile, or does this can this happen on some other tile? I mean, if there's only the problem with type 3 tile. Only type 3? I mean, if it's only like type 3, you could just add a case. Maybe like if it's type 3, you're changing it to type 2, like this. You want to know that if I connect these two, you kind of want to know if they're. So when you connect two nodes like this, what do you want to do here? You need to check if they form a loop. If they form a loop, this is irrelevant. If they don't, here, for example, these two nodes won't form a loop, so this is fine. How do you check if, I mean, there's possibility you can check it with like a DSU if they form a loop, but that's too complicated because you need to delete edges as well. So there must be a simpler solution. If you change it to type 3 and start from type 3 to something else, what you are gaining suddenly is a lot of let's say type 3 doesn't, okay, let's say if it's type 3, I'm not changing. Would this be correct? Oh, that's wait, that's not the type 3. Wait, 0 1 2 3. That's a type 3. Oh no, if AI AJ is type 3, then we don't want to change. Let's say type 3 we don't change. Then we only found one of these, but wait. Oh, this is type 3. Try to construct a loop without using type 3, but I'm not sure. I'm sure it's only type 3. Yeah, I mean, the loop will be only type 3. Okay, let's say, okay, now we don't change type 3, okay, now this would be correct, uh, but why this here, the count is not correct? Where are you supposed to change? You only at one place get 14. But there could be multiple places to get 14. So what will happen? So let me draw an example. How was it to keep forgetting this? Oops, what? 2 is like that. So we have this, we have this, we have this, we have this, and this, then 1, 2, 2, 1, and these loops could make one. The same. 1, 2, 2. 1, 2. 2, 1, 2, 2, 1. 2, 1, 2, 2, 1. 1, 1, 1. 1, 2, 2. I bet there's something with changing it to tile 3. I bet there's some idea here where you can change it. Like there's a long path and then, so it says 14, right? So 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Also this path maybe. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Yeah, so if you do something like this, then you're screwed. This doesn't count because this is a loop here, and like, okay, you start from here, you need to go to some other place, and then, okay, you know what is this distance, you kind of know, you know what is this distance, but this here, you don't know. And when you add here, it's like you are adding 2, you're not just adding 1. You're not connecting this path, so yes, so we're kind of screwed here. What does the values of n matter? The values of n just don't really matter. For the loops, you can iterate over them probably to find the path. So if it's something that is not calculated, you can kind of iterate over it. Oh, actually it matters, and if you're just doing brute force. Hi, Bill. So it matters for n if you're just doing brute force. So what you can do is probably like you can change a tile, and then you can iterate through all of this to find the longest path through all of this, my other function. You can get points as well here, up to probably up to here somewhere, maybe, not sure. But to solve it as a whole, you will kind of need. I'm thinking about these loops. How can we get through them? For those tuning in with just like solved just the first two subtasks for this problem for 60 points, which should be enough to get you on the leaderboard quite high, considering if you have solved this problem. But getting the loops here is just okay. So let's say for each loop we kind of know if that's a loop. We kind of know that here it enters this and here it enters this, so we know that that's a loop. We can check, and we can pre-calculate the length of this loop. And when we change to a tile 3, we know that like if there's some loop that we include, we know how to calculate it. Okay, so kind of for loops is kind of fine, but for this kind of, if we're changing to tile 3, but if we're changing from tile 3, you are creating a loop, and this creation of a loop is what is not fine. Actually, the first example we had here, where we don't have this example, but if I create here a loop, I need to check how if is it a loop, and that's what I'm wondering, how to do it, how to quickly check, because we're always deleting and adding edges. We can't use some DSU or something like that. Is it possible to say that if if two of these nodes are in the same rope from the beginning, if they're in the same rope from the beginning, I don't touch them. So is it just possible to say the following idea? Is this conjecture true? You will never create, I mean, it's just a conjecture. You will never create a bigger rope if two of the points we are connecting are have been in the same row, are in the same row. So if I connect these two nodes that somehow have ended up in the same row, which means that somehow there's a loop, there's some loop here that goes maybe like this, then goes like that, and we want to connect these 2 points, it means that we're just kind of either we're disconnecting the loop, yeah, we're kind of creating this loop, right? And then wait, this point is connected like this, and this connected like this. So what does it happen here? It happens that I go here, then I go here, and then go here, instead of I go here, and then I go here, and then I go here. So I come here, plus 1, plus this here, plus 1, plus this here. So there's like, if this is A, this is the loop, and this is B. So it's A plus B plus L plus 2. If I change it like this, it's A plus 1 plus L plus 1 plus B. So it's the same idea. I think it's the same. It still gets A plus 1, A plus B plus L plus 2. Maybe like fit them into components from the beginning position, just find out if the sections are from the same component for finding out. I can't read this YouTube. If you're for finding out if you're creating a loop, may fit them into components from the beginning position. Yeah, that's what I'm trying to do. Yes, like I'm trying to fit them. Like yes, like create components, but the whole idea is that, like in this case, I'm changing here. I have B plus 1 plus L plus 1 plus A, and then I change something like this node. It's still okay. It's still the same. But if I change something like this, now this creates a loop, and this doesn't. So now it's A plus B plus 1. But still we have to count this idea, this change. So even if, so one way you can make a loop and the other way you can't make a loop. So if you're just doing this, it doesn't make a loop. So okay, so let's say that we know that this here tile, let's say that we know that this tile is, all of these 4 nodes are in the same component, right? We know that. So like, let's say that this tile, all 4 nodes are in the same connected component. If that's the case, then this is the case. One of the configuration creates, 2 of the configuration creates the same length path, and the third configuration creates a smaller length path. But since 2 of the configuration creates the same length path, we just have to know what is the path that is of this component. So if it's if aij is equal to 3, then we have this special case where we check if it's the same component. If same component, then we have to do something. If it's the same component, yeah, I mean it's a hard problem. I say it's not a hard problem, but you have subtasks, and that's why it's so good about this Olympiad. So imagine like this problem could be very well be on tests tomorrow. Very well you could have some problem like this, but you won't be given any subtask. You will be just given, okay, you have all of these three things you have to do and just solve the problem. And now there's no way, even like I wouldn't even start writing such a problem, because there's no way. I know that if you don't get it, you just don't get it. There's no point into starting some hard problem then that's says that the problem is easy. I mean, we just might be overcomplicating it, which is the only sane thing to do, right? For them, it's very easy to say that some problem is very easy, because when you're creating problems, you have a lot of time to think on the problems, right? You I think I think what you're doing is like if you're creating a problem, you're thinking about these problems all week long and more, and there are many people thinking on these problems. So it's not just it's not just I will sit down and I will just solve the problem. The problem, I mean, it isn't something that there's some difficult thing inside of this problem. There's nothing difficult. It's just implementation and edge cases, which is not considered difficult, right? It's considered pain, pain. You know this clip, like the clip where the this clip where he says just so he just says pain. Yeah, that's the problem essentially, right? That's it. It's nothing serious. It's nothing complicated. Trust me. It's just pain. It's just pain. So okay, so we know that maybe this is the case. If I go through this conjecture and I say that, oh okay, so we have some loop created. If it's the same component, we just count twice the length of this component. If it's not the same component, then we don't care. It won't be this. If it's not the same component, if both of these are different components, then we need to find like if that there's a loop here somewhere. And now the loops are just yes, but if implementing, I mean yes, I totally agree with you. I totally agree with you. Because for me, it's not fun implementing something. Like for me, it's much more fun to consider to invent some interesting data structure maybe, and to kind of invent some interesting algorithm, right? Implementation is just implementation. You just have to see edge cases. But 90% of the people that are coming to these competitions do not have the theory knowledge, right? You could ask people coming to ACM competitions, and they will tell you the same thing. They have very limited theoretical knowledge. They only come there to solve implementation problems. So they only just take a problem, see it, and I know like guys that do not have I know guys that like do not at all like learn algorithms or data structures, don't care about that, but are really good in implementation, and they solve sometimes more problems because they would just sit down and code with some like Python script or something. Like they would just make the implementation. I've seen guys copying out, like making 100 lines of code just to make some implementation, right? Just to compute something or to pre-compute something. And it's just, I mean, it's like clearly you can see that that's nothing difficult, in the sense there's no mathematical background here, or there's no computer science background. It's just implementation, but it most of the time gets you much more than theoretical knowledge, which, I mean, it's not. I mean, 100 lines of. I mean, I've seen thousands lines of code just to. Uh, yeah, I don't find them too. I don't find them too. There's many problems in the ACM here judge, which I have been uh, avoiding to absolve, and because of just insane implementation, insane implementation. Yeah, but let's see. Should we? Okay, so there's this idea which changing from tile 3 to tile 2 or 1, it's fine. We will do this. We can do this. But changing from tile 1 to tile. Oh, changing from tile 1 to tile 3 can actually. Also, there's this. There's like ever you need to kind of uh okay, like imagine this case where uh you have something like this. Like imagine. Oh wait, something. Imagine you have some tile like this, and now imagine you have some tile like this. So like you go here, some loop doesn't matter, and gets here. Imagine you have some tile like this, doesn't matter, here ends up somewhere, and here ends up somewhere. Let's say that this is a very long path here. When I switch from this to this, even though I'm switching from tile 1 to tile 2, so in the same family of tiles, I'm adding this loop here. So that's not only switching from the different families of tile. One family is this, one family is this. I'm switching in the same family, and I can add a loop. I can still add this. And this would never be calculated. Like I cannot call. So if I have some loop, okay, I will now pre-compute that this node is in some loop and this node is in some loop, and then I will know, okay, for nodes this and this is some loop. Then I know the length of the loop, and then when I switch here, I kind of know. Okay, so I have this. I can pre-compute loops, and then I can pre-compute the length of the loop, and then I can see if adding something here will add up to this, right? That's kind of fine. Also, this I have to check. So one thing I have to check is if I have a loop somewhere that connects either this or either this. But if I have two loops, then this is not a valid thing, because I need to have a one loop that connects here and one here and here. Now what happens? Oh man, what happens if I have some loop here, some loop like this? Now that's not a loop, but now that's a case where we have to think about adding these. It's just edge cases. It's just edge cases. I don't know. Should I call it? Should I call it? Just finding loops and edge cases. I mean, how much? I have 2.5 hours. I kind of don't want to call it. It's tedious. But it's just edge cases. And I don't believe that there's an easier solution. I don't believe. I believe just that there's some edge case. Should I code it? Chat? Should I code it? How many hours do I have here? How many hours is the live stream? Yeah, the magic. I was thinking about the magic. Let's just discuss let's just discuss magic because I'm not sure. I'm not sure actually. Let me show you something. There's some theorems that I want to discuss here with the magic thing. I mean, we can code this one as well, but it's kind of late already. Let me show you something. So I wanted to test out something like this. Let's say okay, so we have some function, right? We can move this function by saying, okay, this 10 minus x is saying the absolute value of x and 10. So if 10 is here, the absolute value here is 0, right? The absolute difference. And then there's something, this is the amplitude. So if you're having more amplitude, this like gets you a higher point, what we discussed yesterday. So it gets you a higher amplitude point here. But also it gets the wave more thick. How do you say it? Higher width, right? But there's a cool, interesting idea here about this problem, and the idea is that like I could write another function which is like with a higher amplitude. Let's put it something like this, and you see like this function with a higher amplitude will be only overridden at some places here by this smaller amplitude function. Will be only overridden in some places. The other thing, this higher function will actually dominate this small function. But now my conjecture is that this higher function will dominate this lower function everywhere, except on places close to the maximum of this function. Pay attention that the lower function, this here, has a smaller amplitude than the higher function. So we can sort the functions by amplitude, and we can say, okay, the higher function dominates this everywhere. But every lower function will dominate some higher functions, some already functions at some intervals. And what you can do is like at this, like what you can have is like I would assume interval container. And for this interval, we can just binary search on the left and on the right side. And for this interval, we will say that this function is the maximum, the maximum between this and this. I am in the output n lines output for each wizard. In the ith line, the maximum possible total experience gain, the experience gain by 2 positive integers. for an irreducible function. Okay, so the irreducible function, we can represent probably everything with this. Doesn't quite matter. So I would assume that this is the idea of the problem. Like, let's imagine having a third function. Let's imagine that this function is between these two functions. So let's say 60 in the amplitude. And then let's say it's like 14 minus 6 somewhere. So this function dominates the blue function, is being dominated by the red function. Because if we sort them by this, it's like first the blue function will be processed, then this will be processed, and then the red function will be processed. So the green function first will dominate the blue function from this point here to this point. Then the red function will dominate the green and the blue functions in here. So we have some interval, and then we're just making a small insertions inside of the other intervals here. I think that should be the problem. I don't see a way how a smaller amplitude function, let's say with amplitude 8 or 9, I don't see a way, even if I create this function to be very close, like to the red function, I don't see a way how the green function now with a smaller amplitude could ever dominate the red function. Not dominate the red function. Actually, the red function could dominate the green. Wait, I'm confused right now. First, the red function is being calculated, right? Then the green function dominates the red function up to this point. And it dominates the blue function. But my point was that, what was my point? My point was that the green function can never here start dominating the red function. Like can never look like this. Like, you know what I mean. Like the green function must be very big in order to overcome the red function at some point, some other point. So I believe that's kind of the solution to this problem. Just having an interval set and then domination of the function with the higher amplitude is calculated first, then with the lower amplitudes. And we can have either probably one or two sets. Should we make one or two sets? I think one set is enough. I think one set is enough to compute it. So the other thing is outputting this in a P and Q form. It means that you need to know exactly which wizard we're going to take the gain from. And this with our data structure, we will know exactly which wizard we're going to take the gain. The only idea is to be able to binary search across this set. To be able to binary search and to be able, but I kinda wanna eat. Should I do? I'm kinda hungry, so that's the idea of the problem. That's in a nutshell. But I wanna code it. So already 2.5 hours. Alright, this won't be a phase simple problem. Like this would be I'm just okay. I will iterate through the L component, through the I will binary search L. I will binary search R, and then for all of these, I will assign values. I can use interval set already coded, but there's this interval set. If you don't know what is an interval set is, I'll show you. This structure. I mean, it's easy, really easy to call it. You don't have to call it like this. I'm calling it some different way, but it's essentially what you're having a map where you store intervals from L to R that has some value. And when you are adding an interval, you either want to kind of delete, you want to overwrite intervals essentially. I'm not sure if you have seen this function somewhere, but you're storing first one big interval from 1 to n. Then when you add some all this big interval has some value, let's say x for each point, or let's say 3. So each point has 3. Then when the next function will come here, it will binary search where this function will overtake this function, right? Where this maximum. And then what you're doing is like you're cutting this interval into two smaller intervals, which is like 1 to some position L minus 1. Then there's L. Then there's R, where this function will overtake. Then there's from R plus 1 to N. There's this other interval. So this will be the assignment. And this here, let's say that this still remains 3, this remains 3, and this remains this now 10, let's say. Or whatever, you're storing, let's say, the ID of the function here. So function 1, function 1, function 1, and function 2 now. And now when another function comes in, even if the function goes like through multiple intervals, you're just going to do this, right? You're going to overextend. But sometimes the function will come over a whole interval like this, and this interval will be deleted then. So like a whole interval, this interval will be deleted, and then all of the other intervals will remain the same. But one can prove that the amortized complexity of this data structure, amortized complexity, is still of Q. This is the additions of intervals times log of how many intervals we have Q. And this is the implementation of the function. First, we go for the first interval, the ending interval, intervals in between these. Yeah, and that's you're assigning these functions at some intervals, and then when you evaluate, when I have for something I want to evaluate, I will just take the function that is inside the function ID of, if the element is here, of this interval that is, and all of the intervals are actually disjoint. That's very important. There's disjoint intervals. One actually can make this. I mean, instead of using intervals, you can just do lazy segmentary. That will work as well. But sometimes you will want to, if the task, I don't know what is the task, the coordinates go up to 10 to the 9, so you would need to use some sparse lazy segmentary. Which is, again, if you want to call it sparse lazy segmentary, go ahead. If you don't, you can just use this. But I think that's the official. I think it should be. It should that some kind of this can be the official solution of just slicing up the functions according to their strength. But I'm going to eat right now because I haven't eaten. So maybe in the next stream we'll tackle this problem and we'll see what points we'll get for this problem. I mean, I'm satisfied if I get like 60 points for rope for such a simple implementation. It wasn't simple, but it was fun, right? I mean, it is fun until I get edge cases. When I get edge cases, it's not fun anymore. That's my idea. Until I get edge cases, it's fun. I won't submit this because I think the cases are stronger, so I won't get any points. Maybe one can just try for like 70 something points just to go through these cases. Like just that would be insanely simple. Just reuse my function here for calculating the longest thing. But instead of calling it just only once, call it every time you change something. So you change something in the graph and then you call this function and then again and again and again. I mean, it should be fine. It should be n times n times how much you change n times n. So something above this case should work. To here should work. Here it won't work anymore. I don't think it will work. But yeah, that's pretty much it. Hope you enjoyed the stream. I mean, it's kind of disappointing not to solve it the whole way, but for this problem, I will do another stream and solve it because I'm kind of hungry right now, and I didn't expect to get hungry so quickly. But um, I hope that's all right. I hope that's all right. But you know the solution. If you want to try it at home, try solving the magic problem, and then you will. Yeah, don't start. But like tomorrow there's competition, so I will just rest as well. Maybe I won't do anything after the stream. I hope to practice a little bit more, but I mean tomorrow is not the competition. Tomorrow is just a practice day. So we'll just be testing the system. Anyone again, if anyone is in Ljubljana in CERC tomorrow or the next day, or at the competition itself, just come and say hi, because that's pretty cool. I mean, there will be like masters and GMs, all like the whole room will be filled with. If you take a look at Code Forces, like I'm competing with. Um, I will show you. I will show you just for fun. If I go into rating, I will show you with what type of organization. Where is this university? Binary search. Oh, it's G. Yes, this university. I'm competing with these guys. Like, look at them. Look at them. There's no way you can like beat any of them. Like, I want to just beat like the Slovenian teams at least, like get good points there. But like, look at them. Like, all of them are just like either IGMs or masters, and there's no way. And there's like 3 or 4 teams from that university. Like imagine like this is like one team, this is like second team, like this third team. Like I don't know exactly which teams they are, but I don't even know the guys, but like if you just come on, like 2,700 per person per team. Like there's no way you could you could even get close to that. Like just one person. I'm just one person that is competing on Cold Force for my team. The other student is not even competing on Cold Force. So I'm alone. But it should be fun. The problems should be fun, and we'll have fun. So yeah, thank you guys. They're gonna cook. Yeah, they're gonna. That's yes. They are gonna. Uh, I will cook right now. Yes, yes. That's the plan. That's the plan. But thank you guys so much for watching. If I could, maybe tomorrow, Cold Forces Division 2 round, but I'm not sure. I'm not sure because we will be in Ljubljana, so I don't know. We'll see. But yeah, thank you guys so much for watching, and I see you in the next stream as well.